In this video, we're going to talk about our second and last statistical inference tool, confidence intervals. Remember, when we conduct statistical inference, our goal is to draw conclusions about our population parameters, right? And so recall that whenever we collect a sample and we measure individuals on a quantitative variable, and we want to draw conclusions about a population mean, in our sample, we can calculate our sample mean, right? X bar. And X bar is our point estimate for mu, the population mean. Well, you can think of your confidence interval as an interval estimate of your population mean, right? It's an interval of values derived from your sample data that's used to estimate an unknown population parameter. All right, that is what we get when we do confidence intervals. We get an interval estimate. And so, what I want to do in this video is I want to kind of derive the actual formula for confidence intervals, since this is our first introduction to that. So, I'm going to start back to the case where we know a sigma when we're trying to construct or draw conclusions about mu. So, we're going to talk about the confidence interval for mu as if we know our population standard deviation sigma. It says when we collect a sample of size n and we calculate x bar to estimate our population parameter or population mean mu, we know that the sampling distribution of x bar is approximately normal with the mean of mu and the standard deviation of sigma over the square root of n. And we know that's true, especially when we have data, sample data with a large sample size n. Well, in order to contain or obtain a 95% confidence interval from you, we can find the z-score based off of that sampling distribution that yields a middle probability of 0.95, right? So I'm going to go to my standard normal distribution and I'm going to shade off the area under the curve in the middle of the curve or middle of the distribution that constitutes 95% of the area, right? And so what I will want to do here is I want to find the z that creates this. So I want to find this value z here, which is going to be a negative value, and this value z here, right? Well, we've done this before, right? We said, well, if this area in the middle is 0.95 and the total area under the curve is 100% or 1, if I do 1 minus 0.95, I get to 0.05. That's how much we have left over in this tail end of the distribution that's not shaded and on this tail end of the distribution, right? So 1 minus 0.95 is 0.05. Since these two areas are congruent, we can divide it by 2 and we'll see that this is 0.025 and this area up above on the right tail is 0.025. And so since this is a normal distribution, we could go to JASP. I'm going to use the R console here. I'm going to clear that out. And we can use the Q norm function, 0.025 in there. And we can run this code here. And we're going to see that we get to approximately 1.96, right? If I round it to 4 places after the decimal, I'm going to get 0.196. Notice here, I did not put in the mean equals 0 and the standard deviation equals 1. The reason for that is because we were just learning and I wanted you to get used to the function. The default here is for the mean to be 0 and the standard deviation to be 1. So I know in all of the other code that we used before, when we were doing P norm and Q norm, I always told you to type in mean equals 0, standard deviation equals 1, lower.tail equals false, all that stuff there. You don't necessarily have to do that, all right? Because the mean is 0 and the standard deviation is 1, all right? I could also do Q norm of 0.975 because if I go back to my normal distribution there, if this is 0.025 and I add 0.95 to that, this area to the left of whatever this z-score is 0.975, And so what I'll see when my mean is 0 and my standard deviation is 1, if I run that code, I'm going to get to the positive 1.96 approximately, right? So I know that the z that produces the middle 95.95 probability is plus or minus 1.96. All right. So I'm going to use that information to help me construct the confidence interval for mu. All right. Now we're going to always keep this sampling distribution in mind. But what I'm going to do is I'm going to use some probability notation. And I've kind of tried to stay away from a lot of mathematical notation so far in this course. And I think it is kind of necessary so that we can see where this normal distribution, where this confidence interval stuff comes from, not normal distribution stuff. So this is a probability statement. This reads the probability that z is between negative 1.96 and a positive 1.96 equals 0.95, right? That middle probability, that area under the curve. Now I'm going to use this probability statement to help me construct this confidence interval, right? Well, if I'm going to have a confidence interval for mu, I need mu to appear in this interval, right? Notice this is an interval. It says negative 1.96 is less than z is less than 1.96. That's an interval that starts at negative 1.96 and ends at 1.96. I need to get mu in there. Well, the way we started this, and I'll go back to the last slide, I said that, oh, I'm starting with X bar. Well, X bar is normal. And I can convert any normal distribution to a standard normal distribution by looking at Z's. And I'm specifically looking at the Z's associated with the middle 95%, right? That is how we got there, right? So I need to change this Z from being in terms of Z, this interval from being in terms of z to seeing some mu in there. And the way I do that is to use what z equals when I'm looking at the sampling distribution of the sample mean. As we've done this before, z is the observation, which would be my sample mean, minus the mean, which is mu, divided by the standard deviation of the sampling distribution, which is sigma divided by the square root of n. Now I see mu in this interval, right? So I have my confidence interval. But I need to solve this for mu. So now I got to think about my algebra steps to help me isolate mu in this interval here. Well, the first thing I'm going to do is I got to get rid of this division here. So notice it's dividing by sigma divided by the square root of n. I'm going to multiply all three pieces of this compound inequality by sigma divided by the square root of n. Once I do that, I'm going to have negative 1.96 times sigma over the square root of n. When I multiply this middle piece by sigma over the square root of n, it's going to cancel, and I'm going to be left with x bar minus mu. And then when I multiply this, I'm going to be left with 1.96 times sigma over the square root of n. Now remember, my goal is to solve for mu, but I have this x bar, this positive x bar here. So what I'm going to do is I'm going to subtract x bar from each of these three pieces here. So I'm going to have this piece minus x bar, this piece minus x bar, and this piece minus x bar. Now, I said minus x bar, but if we really think about math, it's the same thing as adding the negative, right? And I just wrote my x bar first because that's how it's going to appear in my interval. So notice I have a negative x bar here. So I've subtracted it on this leftmost piece of my inequality here. When I subtract x bar from this part, the x bars are going to cancel and I'm left with negative mu. When I subtract it here, I just wrote it first. So I have a negative x bar plus that 1.96 sigma over the square root of n. Now the last thing for me to do is to multiply or divide by a negative 1. Now this looks like some trickery is about to happen, but it's not trickery. I'm doing two steps in one. Usually when you're dealing with an inequality, when you multiply or divide by a negative, you have to flip the inequality symbols, all right? So when I multiply all of this stuff by negative 1, they both become positive. So negative x bar becomes a positive x bar when I multiply by negative 1. Same thing for this expression here. And these become the opposite signs. But I gotta switch my inequality symbol, so it's gonna be greater thans when I do that. Because we don't generally write our inequalities that way, we would have to reorder our inequality to look as such, which is what I have here. So the stuff after I multiply by negative 1 that was here is now over here. It's not trickery, I promise you. I just skipped the steps because it's not that important. Multiply this by negative 1, it becomes positive. And if I multiply this by negative 1, both of these become positive, right? And that inequality symbol needs to switch to open towards that piece, which it does there. And the inequality here, when I multiply by negative 1, should be pointed towards this and not open. And notice here it's pointed towards it here. All right. Now, if you didn't understand any of that, it is perfectly fine. All right. But this derivation here, so we've derived a formula for the confidence interval, kind of gives us what we expect our mean to be between, what values we expect our mean to be between if that probability is going to equal 0.95, right? If I look at this left part, it's x bar minus 1.96 times sigma over the square root of n. And if I look at that right part of that compound inequality, it looks very similar, but the sign is different. It's x bar minus 1.96 sigma over the square root of n. All right, this is my 95% confidence interval. All right, now we usually don't write it this way in terms of the inequalities here. We just usually give our confidence intervals this way. Confidence intervals always have a confidence level, and that confidence level comes from that probability statement that we just derived everything off of, right? And so since that probability was 0.95, this is a 95% confidence interval. And I'm still in the case for sigma being known. It's going to have two numbers. One of them is going to come from the minus, and the other is going to come from the plus, but it's x bar plus or minus 1.96 times sigma over the square root of n. This is the general form of confidence intervals. They always are composed of a point estimate plus or minus your margin of error. This is our margin of error, the stuff after the plus or minus. The point estimate is our single value that best estimates our population parameter. And our margin of error is actually composed of a product of two numbers, but it's the maximum likely difference between that point estimate and our parameter. The two numbers that make up our margin of error, the first one is our critical value. That critical value comes from, in this case, our normal distribution. All right. So that 1.96 in this example is our critical value. It's a value from the sampling distribution that's aligned with the confidence level. The other number in that margin of error, that product that makes up the margin of error, is your standard error. Sigma over the square root of n is our standard error. It's the standard deviation of our sampling distribution. Now, just as was the case when we dealt with hypothesis testing, this confidence interval is not all that useful in practice because sigma is not known, right? So what we're going to do is we're going to use our sample standard deviation in the place of sigma in our formula for our standard error, which introduces additional variability in our estimate, right? And so to account for that additional variability, we use students' t distribution instead of the normal distribution, all right? And so I know I derive our confidence interval using that z. The one that we're going to use in practice is this confidence interval here. So it's going to be x bar plus or minus some t critical value from our t distribution times our standard error. Remember, this was sigma over the square root of n. Well, now it's the sample standard deviation divided by the square root of n. Now, I have this stuff with this t here. our critical value t, right? Notice this is an alpha over 2. So whenever we have a confidence interval, we have a confidence level. So for instance, that 0.95 was our confidence probability, that confidence level, right? Remember when I went and found the two values of z? I said, well, hey, if I do 1 minus the 0.95, I'll get to the 0.025, right? And well, 1 minus 0.95 is 0.05, and 0.05 divided by 2 was that 0.025 that allowed me to find that point, the 1.96 and that negative 1.96. So we're basically taking 1 minus the confidence level and dividing it by 2. That's the alpha over 2 there. And then we have our degrees of freedom because our t distribution has a degrees of freedom. All right. But this is the critical value from our t distribution, and it aligns with our confidence level. We're going to see a specific example of finding that using JASP a little bit later. And then, of course, we have our standard error here. But this is the formula that you want to know. We're going to do an example of doing this by hand without the computer, and then we're going to rely on the computer to help us do this thereafter. So let's look at actually this example here. It says an educational researcher conducted a survey study on the motivation of high school students. So we've seen this example before. We have a sample of size 500, and we're focusing on the external or extrinsic motivation of students data that we've looked at before. All right, we want to construct a 95% confidence interval for the population mean sum score, all right, on the external motivation scale. Well, for us to do that, we're going to use this confidence interval right here. Notice we need to know X bar, we need to know T, we need to know the standard deviation, and we need to know the mean, right? Well, from the JASP descriptives menu, we can get these three at least. So I'm going to go to JASP, and I'm going to close this out, and I need to open my data set. Do I have it open still? Yeah, this was our data here. Notice this arrow here. So these three dots means you can, if you have your data, if you ever don't see your data or want to see your data and you have this menu open, you can use these three dots to move things, or you can use this arrow here to make that full screen or bigger, and then you can use this arrow here to show your data. All right. I already have my data, and remember we're focusing on this column here, the EM sum. So I'm going to go back and do my descriptives. So by the way, I'm just going to close or remove all of this. I know we have this here, and I can just look at that menu. Let me just start over here. I'm sorry. I'm going to start with descriptives. I'm going to go to EM underscore sum. And notice here, once I do that, it starts calculating some descriptive statistics for me, right? So my mean is 18.232. My standard deviation SD is 4.737. And my sample mean, or my sample size, is N equals 500. All right. So that is my information from JASP. So I have X bar, SD, and N. Now my goal, since I'm constructing a 95% confidence interval, remember this alpha over 2, that comes from looking at the fact that I'm doing a 95%. So my alpha is 1 minus that percentage, which will be 0.05, which is like your significance level from a hypothesis test, right? That's the other place where we use that alpha. It's going to be the exact same one here because there's a relationship between a confidence interval and a hypothesis test. Ooh, this is very interesting, right? All right, so if I do 1 minus this 0.95, I'm going to get to alpha, which is 0.05, or I can think of 100% minus 95% is 5%. That is my alpha, all right? Well, this says I'm going to look at alpha over 2 because in order for me to get the t value, I have a symmetric distribution. I've got to divide it by 2 to know how much area is here, which will help me find this value of t. So if I do 0.05 divided by 2, I get 0.025. All right. Now, this isn't a normal distribution here. It looks like it. This is a t distribution. Now, I want to show you how you can get this value using JASP from the t distribution. Now, as you've seen from before, I'm going to do the R console here. I'm going to just clear output, right? So what we did the first time, I'm going to show you once again. We did Q norm. Notice we did Q norm. What does norm mean? That means it's from a normal distribution, right? And the mean was 0, standard deviation is 1, right? And we got the negative 1.96. Well, what we have to do now is instead of using the normal distribution, we're going to use the t distribution, right? So I'm going to do QT. The t distribution is just identified by the letter t, all right? Which is a little weird, but there it is. I'm going to put the probability first. So I'm going to do 0.025, or you can just say 0.025. And you got to tell it the degrees of freedom from which you're drawing you're specifying your t distribution. So I've got to put this degrees of freedom here because unlike the normal distribution, which is a standard norm, the t distribution you have to put this degrees of freedom. So I'm going to put df equals 499 because our degrees of freedom is n minus 1 for our t distribution, and our n, as you can see up here, is 500. So I'm going to run this code, and I get a negative 1.964729, right? I'm going to try something here. I actually did not try this from before. I did it an alternative way. I'm going to try the lower.tail equals false, and it works, right? So in our notes, I have something slightly different to give me this value here. I don't know why I didn't even think to use lower.tail because that's what we've been using all semester, during our last module. But if I want to know that t value from the upper end of that distribution, I can just use 0.025 and do lower.tail equals false. But this is giving me the value on the t distribution that corresponds or separates the middle 95% from the rest of the distribution. All right? All right, so if I go back to my notes, so I know that this equals negative 1.964729, and this equals 1.964729. It's symmetric, right? So once I get the first one, I'll get the second one. But I did want to put both of these up here. Now notice here, I did this slightly different than I did in JASP. I did 0.9725. I just used the lower.tail equals true the entire time. All right, that is all. So I have all of the pieces that I need. I have X bar, I know my T, I know my standard deviation, I know my sample size. So for me to get the two numbers that make up my confidence interval, all I have to do is put those numbers in their respective places in that formula and do the computations, right? So I have 18.232 in the place of X bar there. I 1.964729, I just use the positive value. I'll put it in its place here for T. 4.737, I put that in its place for the standard deviation. And then we divide by the sample size of 500. If I put that in my calculator, I'm going to get two numbers as my answer. One of the answers is 7.8 approximately, and the other is 18.6 approximately. All right? So these are the two values that I need to be between in order for that probability to equal 0.95. That is my 95% confidence interval. All right? Now, when we do this in practice, we usually don't go through all these formulas and go through this process. And so I do want to show you how you can find this information in JASP. I told you that a confidence interval is a statistical inference tool, right? A statistical inference tool. However, the way we're going to get to it in our JAS software, where it'll do all those calculations for us, is to look at the descriptives module, which we were, using before. In the descriptives module, there's an inference section and then a confidence interval for the mean section. All right. And so I'm going to show you this in JAS. So I'm going to close out this here. In that same example with the EM sum, I'm in the descriptive statistics menu, right? If I go under the statistics menu and if I scroll down, there is actually an inference section here. I can select SE, that's the standard error of the mean, and then I can calculate confidence interval for the mean. The default is to do a 95% confidence interval, and the default is to use your t distribution. That is what we want here. We don't want to use any of these others. All right. Once I do that, this has updated. I see my standard error of the mean of 0.212. So that's our SD divided by our square root of n. But then I see my 95% confidence intervals here. It has an upper number and a lower, an upper bound and a lower bound, right? There's that 17.8 something, and then there's that 18.648 something, right? If I wanted to do a different sized confidence interval, let's say a 99% confidence interval, I can just type it in this box here, and then it's going to adjust my confidence interval. All right. I'm going to change this back to a 95% since this is what we were requesting, and that is our confidence interval there. And so this was the confidence interval that we got, 17.81578, 18.64822. As you're going to see here, we get those same values, right? This is the interpretation that we usually give when we interpret a confidence interval. We say that we are 95% confident, so you need to tell how much confidence you have, that the population mean extrinsic motivation sum score is between 17.8 and 18.6 points. I guess I should have said points. Well, what's the sum score? So that's the units there. So sum score is between 17.8 and 18.6. All right. And so that is how we come up with these confidence intervals. Once again, the 95% is the most common in education research as well as most social science fields. Sometimes, depending on how our data, our studies are structured, we may change that confidence level to a different value. But you want a lot of confidence, high confidence. One of the things that we want to do or to stress here is, what do we really mean when we say we are 95% confident? All of this stuff relies on a sampling distribution. Okay? And whenever we constructed sampling distributions, we said we would go out to the population, take a random sample, calculate our sample mean, or our statistic, do that over and over and over and over again, right? And that sampling distribution is just the distribution of all those possible outcomes that we got every time we did those resamplings and calculated our statistic. The same thing happens when we do this confidence interval stuff because it's based off of the sampling distribution. What we're saying, what we really mean, is that if we repeat this study over and over and over again, that should literally say many, many times. So if we were to repeat this study many, 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 many times, because, go out, get our sample of 500, have them fill out that survey on extrinsic motivation and intrinsic, get those sum scores, construct this confidence interval. And we did that over and over and over and over again. We expect that 95% of the confidence intervals that we construct, we expect 95% of them to actually contain the population mean mu. All right? When we conduct the studies in practice, we only have one of those possible confidence intervals that we actually construct. And we hope that it's one of the 95%. All right? And so that's why we want our confidence level to be high, because we want to be in one of the ones that actually captures our population parameter. Because we do know that some of those, if we repeatedly resampled and did our study, you may end up with a confidence interval that does not contain your population mean, right? 95% of them will, 5% of them won't. We're doing one study. We hope we're in one of the 95% of those studies. That is what we mean when we construct confidence intervals and say we are 95% confident. All right? Now, what I want you to notice is something interesting. I want to go back to the results here. I'll go back to this. I'm sorry for scrolling so much. This confidence interval here, right? We are 95% confident that the population mean extrinsic motivation sum score is between 17.8 and 18.6, right? 17.8 and 18.6. I just want to look back and see what our results were whenever we did the hypothesis test. So I'm going to scroll back in our notes. These were the results of our hypothesis test, the one sample t-test. And remember, our hypothesis test, we used, oh, that's not the one. For our hypothesis test, we used alpha equals 0.05. This alpha of 0.05 aligns with a 95% confidence interval. Because if I change this to a percentage, that will be 5%. And so that aligns with the 95% confidence interval, right? When we did this, we failed to reject that our population mean was different than the value 18, right? So we said we would fail to reject, which means it's possible that our sample mean could possibly still be 18. We're still just unsure because we haven't gathered enough evidence, right? Well, when we did this confidence interval here, notice that 18 is in that confidence interval. So what you're gonna notice, and I have some examples in the practice problems for this module. You're gonna notice that when the value of your hypothesis test is in your confidence interval, you're gonna fail to reject. Those are equivalent things. But if what the value that's in your null hypothesis is not in your confidence interval, you're gonna reject the null hypothesis. That's a quick little preview of a couple of the problems that I'm going to walk you through while you're doing your homework. But that's some of the stuff that you'll notice as you do more and more confidence intervals and hypothesis tests. All right, I'm going to stop here with this video. I think that gives you a good overview of confidence intervals for the confidence interval for your population mean mu. Once we move forward, we'll probably just give the formula. We won't go through this full process because as we start to increase or do more and more hypothesis tests and confidence intervals, the formulas get a lot more complicated. There's a lot more requirements. I spent a lot of time. I know these videos are a lot longer than the other videos, but I want you to really, really understand confidence intervals and hypothesis tests. I will be honest with you. We're in a one sample case. A lot of published research there's very few published research in this day and age that focuses on a one sample problem or one population mean. All right. But I spend a lot of time doing this because a lot of stuff just flows from your understanding of this. So if you can really understand the hypothesis test components as well as the components of your confidence intervals, as we add more or get more and more um, content into our course, hopefully that information would translate to these other areas where we may have to tweak some things in order to come up with a test statistic and things of that nature. All right, but that is all for this video. I look forward to us learning more hypothesis tests, more research designs that require different types of hypothesis tests and confidence intervals. But the bulk of those two topics we have now nailed down, and we're done. All right, and so I'll stop here, and I'll see you during our next week's content.